Now, B, intrinsic geometry, exterior algebra, extended to R3, curvilinear coordinates, and R4. Now, B, part 3, miscellaneous topics in intrinsic geometry, extended to extrinsic geometry also. B, part 3, differentiable manifolds. Part 3, lecture 2. I advise you, I recommend to study lecture 1. Properties of the Lie bracket, contravariant components. Now, our focus is contravariant components. Now, the global property, a vector x that belongs to the vector space. You see, xi is the contravariant components, and this is partial of ui is xj. That's a very important property, okay? This belongs to R. Now, on the other hand, this function f applied to x is fxi partial xi, so this belongs to the manifold, vector field to the manifold. Now this is local. You see P over here, this is local. So xi, this is a basis, this is covariant basis, this is contravariant components. At point P, this vector field belongs to the manifold. Now, again, f xp is local. You see, this is local, this belongs to the manifold. Now, xp applied to f is xi partial f respect to xi at point P belongs to R. Attention now, xp applied to f is a scalar, okay? xp, xj, you see, just you can copy from here. You see, this is just xj belongs to R. So, xp applied to j belongs to R. Now, attention now. Now we'll focus on points that belong to the chart. The chart. You see there's the chart, there's a point P. This is a small region around point P, which the coordinates belongs to R3 in this case. So U prime, U2, and U3, they belongs to R3. This is important. Belongs to R3. And don't forget, this point P is over here, at this place over here, okay? So, the local expression for the Lie bracket on the chart is the region. Chart is the region, the small region, which leaves, you see, the tangent vector space. Now, consider vector field locally on a coordinate neighborhood, the chart u, xi. Xi belongs to the manifold, okay? Don't forget that, at the same point P. So xi is yj, the local expression for the Lie bracket on the chart. Don't forget, this is a chart. Okay. Now the Lie bracket applied to f, that's the definition, okay? It's x applied to y, f minus y, xf. Now I substitute now by the components, yj and partial of xj, okay, minus y applied to x, the vector, okay? These are components. Now, xi, partial of xi, yj minus this just copy from here to here. Again, there's a vector field. These are two functions. Vector field, a green here, you see, they are two functions. So I can expand, okay, using Leibniz rule, is the product rule or Leibniz rule. Expand yields. Now it's quite easy. Here you just expand this, okay, and then expand that. You just look at here, copy, and compare. Now, xi, now it's easy. This is partial yj xi, if I just follow from here, okay, this is equal to this line here, you see. Now attention now, you see this green mark here, you see this green mark here, I is dummy, j is dummy, so I can swap, you see, I can set j here and j here, y here and y there. So that's quite easy here. So I have partial f of xi, you see, this is j, I swap to I, minus this I maintain the same. So I can move from here to here, okay, this is partial xi and this is partial xi, because here I swap it. Now, clearly, you can see that this parenthesis over here is a function that belongs, attention now, to the infinite differentiable functions. These are the basis vector, belong to the vector field, the vector space. Consequently, this Lie bracket belongs to the vector field. Now it's on the chart because it's locally. You see, this belongs, this is the chart. Now, basis vector fields, this is a final, okay? This is a final what I want to derive here. Now, there is a very important property, okay? This is a Lie bracket of the covariant basis, xi and xj here. This is equal 0. Let's check. You see, let's apply the definition of Lie bracket, okay? Just a straightforward. Now this is partial xi, this here minus this there. So since the function is smooth, I can swap this derivative over here, and then I think this xi partial xj here, okay? I can swap this and this. That's why this is equal to 0. Attention, linearity. You see, x, this is f plus g. I just represented the sum. X alpha f is alpha xf, where alpha now belongs to R. Attention now, alpha belongs to R. Now the product, this will derive in lecture 1. You see, this is just, I can expand like this. It's Leibniz rule, or the product rule. Now, properties of this case, or compatibility conditions, okay? You just copy here, okay? That's what we did, okay? It's f plus gx, the sum, f, this case, x plus y is also there. Now 1x, this one is alpha. You see the alpha over here, okay, this alpha over here, I just set 1 here. This belongs to the vector field, okay, the manifold. Now fg, I just wrote that. This is the Lie bracket, the global. Attention, this is global. When I set p over here is local. X, that's a very, very important. xf belongs to the differentiable functions, belongs to the C infinity. But the swap, you see, xf fx. Fx just belongs to the vector field. That's very important. Please don't forget to subscribe and also share with your group. And I would like also to emphasize and to say many, many thanks for who is putting comments, okay? And I feel quite motivated just to display this work, okay? That's it.